Hello, chemistry students. Here is your teaching video for Chapter 13 Notes, Day 5. You're going to be starting in your outline at sunlight consists of, and we are going to finish the outline today. So, sunlight consists of white light, or kind of the definition of white light is that it is light with a continuous range of wavelengths and frequencies. The color of the light is characteristic of the wavelength and the frequency. So, because sunlight consists of a continuous range of the wavelengths and frequencies, we get a spectrum that occurs when sunlight passes through a prism. And you've actually seen this before. If you have had a sun catcher in a window, the rainbow that it causes somewhere. Also, the rain droplets in the sky when you see a rainbow in the sky. Okay, those are both this spectrum. So what's happening here is the different wavelengths separate into a spectrum of colors. Again, an example of when you've seen this is a rainbow. For a rainbow, what's separating the light are the rain droplets in the atmosphere. Now, you also hopefully have learned that the order of the colors in a rainbow is always the same. So that order is always red, orange, yellow, green, blue, and violet, often abbreviated Roy G. Biv. I left the I out, that's indigo, because indigo really is a combination of blue and violet. When you talk about this spectrum of our visible light, the red has the longest wavelength and the lowest or smallest frequency. So this similar type of thing is going to happen when you excite atoms with electricity. Okay? So an atomic emission spectrum happens. This happens when an electric current is passed through a gaseous element. So we just mean an element in its gas state of matter. The electrons of the atom are energized and the release of this energy causes them to emit light. In fact, in our classroom, that's what happens when we turn on the fluorescent light bulbs, right? The fluorescent light bulbs are not giving off any light, but when we turn them on and pass that electric current through the gaseous element that's inside that light bulb, the electrons of the atoms are energized. They're going to jump up to a higher energy level where they're unstable. When they fall back down, they're going to release that energy, and that means that they're giving off light. If you've ever broken a fluorescent light bulb, you've probably heard it pop. It's popping because there is pressurized gaseous element inside that light bulb. So kind of more specifically, what's happening here, when the atoms absorb energy, because they have to absorb energy to jump to a higher energy level, their electrons move to a higher energy level. The electrons lose that energy by emitting or giving off light. When they return, to lower energy levels. All right, the energy absorbed by an electron, for it to move from its current energy level to a higher energy level is identical to the energy of light emitted by the electron as it drops back to its original energy level. So all I'm saying here is the amount of energy that that electron absorbs as it jumps from a lower energy level to a higher energy level. That amount of energy is exactly the same amount of energy that that electron gives off as it falls back down from that higher energy level back to its original energy level. So it's this idea, remember when we talked about Bohr's model, we talked about the idea that it was like a ladder and that there was a certain distance or amount of energy between energy levels. All we're saying here is that distance is the same whether I'm jumping to a higher energy level or falling back to a lower energy level. That distance between or amount of energy between energy levels stays exactly the same. So then what is a line spectra or a discontinuous spectra? Now the word discontinuous means not continuous. That means it's not going to look like the rainbow, okay? It's not going to have all those different colors. So when you take this light that's given off by the electron and you pass it, it's passed through a prism, a spectrum consists of a limited number of narrow lines of light. The wavelengths of these, they're called spectral lines, are characteristic of the element and make up the atomic emission spectrum of the element. So what we're saying is, so we have a bulb, let's say, with just one particular element in it. And we pass an electric current through it, and those electrons get excited, and they jump to those higher energy levels, but they're unstable, so they fall back down. And as they fall back down, they give off that light. If we take that light and we pass it through a prism, instead of getting that rainbow, we're going to get just some specific lines of specific colors. And that set of lines is specific to that particular element. Okay? Each line corresponds to exactly one wavelength of light given off by the electron of that element. So each line is a different wavelength. And like a person's fingerprint, no two elements have the same atomic emission spectrum. So Fingerprints for people uniquely identify people. Atomic emission spectrums uniquely identify particular elements or atoms on the periodic table. So because of that, this atomic emission spectrum can be used to identify elements. Now, maybe you've never thought about it before, but in earth science class, you probably learned about the composition of stars in outer space, right? That they know that this star is made up of hydrogen or helium or iron or the different elements that make up these stars. Was that because we sent a probe out to that star and gathered a sample of that star and brought it back to Earth and identified it or examined it? Absolutely not, right? There's no way that we can get to the stars that we've studied and get back with a probe, let alone have the probe be able to survive getting to the surface of a star. Okay, so how is it that scientists know the composition of these faraway stars? They use this atomic emission spectrum. So this is how we know the composition or makeup of the stars in our universe. Because scientists study the light that that star gives off. And that light, the atomic emission spectrum of that light, so when I take that light and pass it through a prism, the lines that I get, those lines are specific to special or specific atoms. And so I can use those lines to identify the atoms. So for example, here's what the atomic emission spectrum looks like for hydrogen, helium, neon, sodium, and mercury. Okay, so if you had a hydrogen light bulb and you passed that light through a prism, you would get these lines of light that you see here for hydrogen. Notice those lines are different than the lines you get for helium, different from the lines you get for neon or sodium or mercury. Okay, so each element has its own unique set of this atomic emission spectrum, right? This is an atomic emission spectrum. And this is what allows scientists to know what stars are made of. Because they measure, they study the light that star is given off. They pass it through prisms and they get spectrums like this. And they say, oh, that spectrum exactly matches sodium. So that star must be made of sodium. Okay, so these are what atomic emission spectrum look like. Notice they're different than what we get in a rainbow. Right, in a rainbow we have all the colors of light. Okay, here we don't necessarily have all the different colors of light, right? Sodium doesn't have any red, doesn't have any blue, it doesn't have any violet. Okay, so we don't necessarily get all the different colors of light in an atomic emission spectrum. And each atomic emission spectrum is unique to that element. Hydrogen's atomic emission spectrum always looks like this. Sodium's always looks like this. Okay, there's no variety with this. So how is this kind of related to the quantum concept and the photoelectric effect? Okay. According to the laws of classical physics, the atomic emission spectrum of an element should be continuous. Which means it should look like a rainbow. Okay, but we know that it doesn't. So that was a problem. So classical physics couldn't explain the emission spectra, which is just the plural of the word spectrum, of atoms. Because they were line spectra instead of continuous spectra. They were discontinuous. So the scientist who worked to explain that was Max Planck. Okay? And he was really initially trying to describe why iron first appears black, then red, then yellow, and then white as its temperature increases. And again, this was something that people were familiar with, not just scientists, but all people. Iron is primarily the metal that's used by blacksmiths. And remember, in the 1800s and early 1900s, blacksmiths made all kinds of things for people in society. They made harnesses for horses. They made horseshoes. They did all these things. Blacksmiths, every town had a blacksmith. So pretty much everyone would have seen a blacksmith working. And they knew that the blacksmith, the metal they started with, would start out as black. Eventually it would kind of start to glow red, yellow, and white. And based on what color it was glowing, the blacksmith would know whether or not the metal was ready to do whatever they needed to do with it. Okay, and scientists weren't able to explain why this was happening. So Max Planck is going to try to explain it. He could explain the color changes if he assumed that the energy of a body changes, and we don't mean like a human body, but we mean like a body of metal, only in small, small, discrete units, or quanta. So he's saying energy can only change in very specific amounts. They're small amounts, but they're small specific amounts that he called quanta. So he came up with an equation, and we saw this equation on a ChemQuest, that E equals HV. Okay, what are these? So Planck's constant, which is H, has a value of 6.626 times 10 to the negative 34th joule seconds. So that's what the H stands for. It's his constant. And this equation is saying that the energy of a quantum is equal to h times this constant times frequency. So this is saying that a small energy change involves the emission or absorption of low frequency radiation, and a large energy change is because of a high frequency radiation. I don't know where that stopped again. So an explanation of atomic spectra. The atomic emission spectra was known before the Bohr's model explained it. It predicted specific values of frequencies which agreed with experiments. In the ground state, the electron has the lowest possible energy. We say the atom's in its ground state. The principal quantum number, n, is 1, and we excite the electron, and that electron moves to n equals 2, 3, 4, or 5. So when we excite it, remember, we provide it with a source of energy, often from electric current. A quantum of energy in the form of light is given off as that electron drops to a lower energy level. This drop occurs in a single step called an electronic transition. The light emitted or given off by an electron moving from a higher energy level, or we'll just say from a higher to a lower energy level, has a frequency directly proportional to the energy change of the electron. And so each line that we see in that atomic emission spectrum, each line is produced by a transition of an electron. Okay, so again, this whole directly proportional thing goes back to Planck's equation, which said that the frequency and energy were directly related. And what we're saying here is that each line in this atomic emission spectrum back here, each of these lines is because an electron has jumped to a higher energy level and is releasing a specific frequency of light, which is a specific energy of light. So each line is that electron moving from a higher to a lower energy level. So we want to take a look at the emission spectrum of hydrogen, which is on page 380 in your textbook. It's figure 13.17, and I have it here. Okay. You'll notice in this emission spectrum of hydrogen, okay, that there are 3 groups of lines in the emission spectrum. of hydrogen atoms. Okay, so again, notice we have these three groups of lines. It's kind of hard to see. It's not really kind of there really that we're talking about. We're talking about the three groups of lines up here. Okay. This group of lines in the UV end is called the Lyman series. And what's happening here, if you look at those, okay, so this is our Lyman. Notice that every single time we're transitioning back to the n equals 1 energy level. So in the Lyman series, the transition of the electron is from a higher energy levels to the lowest energy level. N equals 1. We can't see the Lyman series in the atomic emission spectrum. The part we see is the visible spectrum, which is called the Balmer series. Again, that's these here, and notice this time we're transitioning not to the first but to the second main energy level. So these are the transition of the electron from higher energy levels to the n equals 2. Also notice that this is a smaller change in the electron energy. Right, so this distance here, that's smaller than the distance here. The infrared range is called the Passion series, and this is the transition from higher energy levels to the n equals 3. Right, so the Passion, again, this time, every time we're ending in the n equals 3 energy level. Lastly, notice that the lines in each group become more closely spaced at increased values of n because the energy levels become closer together. Okay, so all we're saying here is these lines kind of get closer and closer together, okay, because those the energy levels are also closer together in terms of energy. So there were some problems with the Bohr model, as we're kind of familiar with, but we're going to kind of review those again. So the problems with the Bohr model is that it didn't explain the emission spectra of atoms with more than one electron. Remember that Bohr had purposely chosen hydrogen because it was simple and only had one electron. However, when he tried to apply it to more complicated atoms with more electrons, it didn't work. And it didn't help explain how bonds occur to form molecules. So it couldn't help explain like why certain atoms would bond together and others would not. The last thing we want to talk about is the German scientist Werner Heisenberg, who came up with the Heisenberg uncertainty principle, which states that it's impossible to know both the velocity, which is just the scientific name for speed, and the position of a particle at the same time. So specifically, the particle we're concerned about are the electrons. And this concept is important to quantum mechanics. So this is really even true when you think about like a car traveling on the road, right? If I have a car traveling down M66, I can know one of two things about the car. I can know how fast it's going, so let's say it's going 55 miles an hour. Or I can know where it is. But as soon as I know where it is and say it's here, because it's going 55 miles an hour, it's not actually there anymore, right? It's somewhere else. And so that's what Heisenberg was getting at. He was saying, because an electron is constantly moving fast, I'm never going to be able to say exactly where it is. If I say exactly where it is, it's not there anymore. If I know how fast it's moving, I don't know exactly where it is. So he just says that those two things, you can kind of know one or the other, but you can't know both of those things at the same time. And that's an idea that's important to quantum mechanics. It's why the quantum mechanical model is about probability, how likely or probable it is to find an electron in a particular three-dimensional space, as opposed to saying the electron is specifically here or there. So you do have homework this evening. It's on page 383. You're supposed to answer questions 16, 18, and 19. Have a good evening.